Welcome to our exploration of LiDAR remote sensing and its wide-ranging applications. In this video, we'll journey through the fundamentals of remote sensing, the evolution of LiDAR technology, and how it's transforming fields from forestry to urban planning and geoscience. Whether you're a student, researcher, or simply curious about how we map and analyze our world, this series will provide a comprehensive, accessible introduction. Let's begin by understanding what remote sensing is and why LiDAR stands out as a revolutionary tool in this domain. Remote sensing refers to the science of obtaining information about objects or areas from a distance, typically using aircraft or satellites. It began with aerial photography using balloons and planes, evolving into sophisticated electronic sensors. Today, remote sensing covers a broad spectrum, including visible, infrared, and microwave wavelengths. This technology allows us to map, monitor, and analyze the Earth's surface, even in places that are hard to reach. Its applications range from environmental monitoring to urban planning and disaster response. Journey of remote sensing started with simple aerial photographs taken from balloons, kites, and early airplanes. These images were invaluable for mapping and military reconnaissance, especially during the World Wars. However, early methods had limitations. They depended on weather conditions and produced analog images that were hard to analyze quantitatively. The field advanced rapidly with the introduction of electronic sensors and digital imaging, paving the way for more precise and versatile data collection. Remote sensing relies on the electromagnetic spectrum, which includes visible light, infrared, and microwave regions. Different sensors are designed to detect specific wavelengths, allowing us to gather diverse information about the Earth's surface. For example, visible bands help us see what the human eye can, while infrared and microwave bands reveal details invisible to us. Understanding the spectrum is key to choosing the right sensor for each application, from vegetation analysis to mineral exploration. There are two main types of remote sensing systems: passive and active. Passive systems, like traditional cameras and multispectral sensors, rely on sunlight reflected from the Earth's surface. Active systems, such as radar and LiDAR, emit their own energy and measure what bounces back. This means active sensors can operate day or night and are less affected by weather conditions, making them especially valuable for consistent data collection. Multispectral remote sensing collects images in several broad wavelength bands, typically in the visible and infrared regions. These sensors, mounted on aircraft or satellites, record how different surfaces reflect sunlight. By analyzing these reflections, scientists can distinguish between various materials such as rocks, soil, and vegetation. Multispectral data is widely used in agriculture, forestry, and geology, providing essential insights for resource management and environmental monitoring. Thermal infrared sensors detect heat emitted by the Earth's surface, rather than reflected sunlight. This capability is crucial for applications like geologic mapping and mineral exploration, as different materials emit heat differently. For example, silicate rocks have unique thermal signatures that can be identified using specialized sensors. Thermal data also helps in monitoring urban heat islands, volcanic activity, and even detecting wildfires. Launch of the first Earth-observing satellites in the late 1950s marked a new era for remote sensing. Satellites like Landsat, SPOT, and IRS have provided continuous global coverage for decades. These platforms carry multispectral and thermal sensors, enabling large-scale monitoring of land use, vegetation, and environmental changes. Satellite data is now indispensable for scientists, governments, and industries worldwide. Landsat program, launched by NASA in 1972, revolutionized remote sensing. With a series of satellites equipped with advanced sensors, Landsat has provided detailed images of the Earth's surface for over 50 years. These images have been used to track deforestation, urban growth, and agricultural trends. Landsat's legacy continues today, offering free, accessible data for researchers and decision-makers everywhere. Hyperspectral remote sensing takes things a step further by capturing hundreds of narrow, contiguous spectral bands. This allows for near-laboratory quality analysis of surface materials, as each pixel contains a detailed spectral signature. Hyperspectral data is especially powerful for identifying minerals, mapping vegetation species, and detecting subtle environmental changes. Instruments like AVIRIS and Hyperion have set new standards in Earth observation. Recent trend in remote sensing is the integration of multiple sensor types on a single platform. For example, NASA's Goddard Space Flight Center developed an airborne imager that combines LiDAR, hyperspectral, and thermal sensors. This synergy leverages the strengths of each technology, providing richer, more comprehensive data for applications like forest mapping, urban analysis, and environmental monitoring. LiDAR remote sensing uses microwave energy to illuminate the Earth's surface and measure the reflected signals. Unlike optical sensors, radar can operate day or night and penetrate clouds, making it ideal for all-weather observation. Radar images reveal surface roughness, moisture, and even subsurface features in some cases. This technology is widely used in geology, agriculture, and disaster monitoring. Understanding radar images requires knowledge of several key parameters: incidence angle, dielectric properties, polarization, and wavelength. The incidence angle affects how features appear, sometimes causing foreshortening or layover in mountainous areas. Dielectric properties influence how much energy is reflected, while polarization and wavelength determine the sensor's sensitivity to different surface types. Mastering these concepts is essential for accurate radar image interpretation. Radar remote sensing has found applications in many fields. In geology, it helps map rock types and fault lines. In agriculture, radar can monitor crop growth and soil moisture. It's also invaluable for disaster response, such as detecting flood extents or earthquake damage. The ability to see through clouds and operate at night makes radar a reliable tool for continuous Earth observation. LiDAR, or light detection and raying, is an active remote sensing technology that measures distances by timing how long it takes for a laser pulse to travel to an object and back. LiDAR can be mounted on aircraft, drones, or ground vehicles, and is renowned for its ability to generate highly accurate three-dimensional models of the Earth's surface. This precision has made LiDAR a game-changer in mapping, forestry, urban planning, and more. Sets LiDAR apart from other remote sensing technologies is its ability to collect dense, precise 3D data, even in areas with dense vegetation or complex terrain. Unlike passive sensors, LiDAR works day or night and is less affected by lighting conditions. Its high-resolution point clouds enable detailed analysis of forests, cities, and geological features, supporting applications that require fine-scale measurement. LiDAR data has been collected from diverse locations around the world, including Hawaii, California, Texas, Brazil, Canada, Ghana, and Haiti. These datasets cover a variety of landscapes, from forests and mountains to urban areas and coastlines. By analyzing LiDAR data from different environments, researchers can develop and test new methods for mapping, monitoring, and managing natural and built environments. Book LiDAR Remote Sensing and Applications stands out for its comprehensive approach. It not only explains the principles and data processing methods of LiDAR, but also provides hands-on projects and real-world case studies. With over 500 references and 183 figures, it serves as a valuable resource for students, professionals, and researchers seeking to deepen their understanding of LiDAR technology. Dr. Pinliang Dong and Dr. Chi Chen are leading experts in LiDAR remote sensing. Dr. Dong, professor at the University of North Texas, specializes in GIS, digital image analysis, and LiDAR applications in forestry and urban studies. Dr. Chen, professor at the University of Hawaii, focuses on LiDAR data processing and environmental applications. Their combined expertise ensures the book is both authoritative and accessible. This resource is designed for a wide audience. Undergraduate and graduate students in geography, ecology, GIS, and remote sensing will find it an excellent textbook. Professionals in industry and academia can use it as a reference for practical applications. The step-by-step projects are especially helpful for those looking to apply LiDAR data in real-world scenarios, regardless of their prior experience. Processing LiDAR data involves several key steps: filtering, classification, and spatial interpolation. Filtering separates ground points from non-ground points, while classification assigns labels to features like buildings or trees. Spatial interpolation creates continuous surfaces, such as digital elevation models, from discrete LiDAR points. Mastering these techniques is essential for turning raw LiDAR data into actionable information. Book features 11 hands-on projects, most of which use Esri's ArcGIS software. These projects guide users through basic LiDAR visualization, terrain modeling, and advanced analyses like population estimation and sand dune migration. The included datasets, covering over 4.4 GB, allow learners to practice and develop their skills using real-world examples from diverse locations. LiDAR is a powerful tool for forestry, enabling precise measurement of canopy heights, biomass estimation, and individual tree mapping. By analyzing LiDAR data, researchers can assess forest health, monitor disturbances like hurricanes or lightning, and support sustainable management. The book includes case studies from Pennsylvania, Florida, and Ghana, showcasing LiDAR's versatility in diverse forest environments. In urban environments, LiDAR is used for road and building extraction, 3D reconstruction, population estimation, and change detection. High-resolution LiDAR data helps city planners, engineers, and emergency responders make informed decisions. Projects in the book demonstrate how LiDAR supports urban analysis in places like Denton, Texas, and Surrey, Canada. After natural disasters, LiDAR data is invaluable for assessing building damage and road blockages. Its ability to quickly generate accurate 3D maps allows responders to prioritize resources and plan recovery efforts. The book includes examples from Haiti and Texas, illustrating how LiDAR aids in disaster response and resilience planning. LiDAR is equally valuable in geoscience, where it helps map landforms, monitor sand dune migration, and analyze geological structures. By capturing fine-scale topography, LiDAR supports studies of tectonic activity, surface hydrology, and volcanic features. The book's projects include measuring dune movement in New Mexico and analyzing rock layers in Utah. LiDAR data comes in various formats such as LAS and ASCII, each with its own advantages for storage and processing. Ensuring data accuracy is critical, as even small errors can affect analysis results. The book discusses best practices for data management, quality control, and the use of reference datasets to validate LiDAR-derived products. Typical LiDAR system consists of a laser scanner, GPS, and an inertial measurement unit, EMU. The laser emits pulses, the GPS records position, and the EMU tracks orientation. Together, these components enable precise georeferencing of each LiDAR point, ensuring the resulting 3D models are both accurate and reliable. LiDAR works by measuring the time it takes for a laser pulse to travel to a target and return. This time-of-flight measurement, combined with the speed of light, allows for precise distance calculations. By scanning across an area, LiDAR systems collect millions of points, creating detailed representations of the Earth's surface and objects on it. Several factors influence the accuracy of LiDAR data, including sensor calibration, flight altitude, and environmental conditions. Careful planning and calibration are essential to minimize errors. The book provides guidance on best practices for data collection and processing to ensure high-quality results for any application. Visualizing LiDAR data is a crucial step in analysis. point clouds can be rendered in 3D, revealing terrain, vegetation, and structures in stunning detail. Specialized software allows users to filter, classify, and extract features, making it easier to interpret and utilize the data for specific purposes. LiDAR data is often used to generate digital terrain models (DTMs) and digital surface models (DSMs). DTMs represent the bare ground surface, while DSMs include buildings, trees, and other objects. These models are foundational for applications in hydrology, urban planning, and environmental management. In forestry, LiDAR is used to create canopy height models which reveal the structure and density of forests. By comparing leaf-on and leaf-off data, researchers can assess seasonal changes and identify disturbances. These insights support forest management, conservation, and biodiversity studies. LiDAR's high resolution enables the identification and mapping of individual trees. This is achieved through advanced algorithms that analyze point cloud data to isolate tree crowns and estimate attributes like height and biomass. Such detailed information is invaluable for ecological research and forest inventory. Beyond individual trees, LiDAR supports area-based modeling, where forest attributes are estimated for larger plots or regions. This approach is useful for large-scale biomass estimation, carbon accounting, and monitoring forest health across landscapes. The book provides practical examples of area-based modeling using real LiDAR datasets. LiDAR data is essential for creating detailed 3D models of urban environments. By extracting building footprints and heights, city planners can visualize skylines, simulate shadows, and plan infrastructure. These models also support emergency response, transportation planning, and smart city initiatives. By analyzing the volume and area of residential buildings extracted from LiDAR data, researchers can estimate population densities in urban areas. This method provides more accurate and up-to-date information than traditional census techniques, supporting urban planning and resource allocation. LiDAR enables precise change detection by comparing datasets collected at different times. This is particularly useful for monitoring urban development, detecting unauthorized construction, and assessing the impact of natural disasters. Automated algorithms can quickly identify changes, saving time and resources. After disasters like earthquakes or hurricanes, LiDAR data is used to assess building damage and road blockages. Its rapid, high-resolution mapping capabilities enable authorities to prioritize rescue and recovery operations, ensuring help reaches those who need it most. In geoscience, LiDAR is used to map landforms such as sand dunes, river valleys, and fault lines. Its ability to capture fine-scale topography reveals subtle features that are often invisible in traditional maps. This information supports research in geomorphology, tectonics, and environmental change. LiDAR data is invaluable for studying surface hydrology, including mapping floodplains, modeling water flow, and identifying drainage patterns. Its high-resolution elevation data allows hydrologists to simulate water movement and assess flood risks with greater accuracy than ever before. LiDAR's precision makes it ideal for analyzing geological structures such as folds, faults, and volcanic features. By generating detailed 3D models, geologists can study the formation and evolution of landscapes, assess hazards, and plan field investigations more effectively. Environmental managers use LiDAR to monitor changes in land cover, assess ecosystem health, and plan conservation efforts. Its ability to provide up-to-date, high-resolution data supports informed decision-making for sustainable resource management and habitat protection. LiDAR technology continues to evolve, with advances in sensor miniaturization, data processing, and integration with other remote sensing methods. The future promises even greater accessibility, accuracy, and application diversity, making LiDAR an indispensable tool for understanding and managing our world. Summary: LiDAR remote sensing is transforming the way we observe, analyze, and manage the Earth's surface. Its unique ability to generate accurate 3D data supports a wide range of applications, from forestry and urban planning to geoscience and disaster response. As technology advances, LiDAR will continue to play a vital role in research, industry, and environmental stewardship. Thank you for joining us on this journey through the world of LiDAR remote sensing.